Right. Good morning. Any questions? Any comments? So I'll start talking about Ginzburg-Landau formalism, and you'll see it's kind of like a friendly way of tipping your toes in quantum field theory and techniques you can use in quantum field theory. So this is. How many people have ever heard of Ginzburg-Landau formalism? Have you ever used it? You just heard it, right? Okay, good. It is for some reason not as much known, but let's see. So first, I want to introduce something called condensation energy. Let's talk about thermodynamics in condensed matter. And the idea is, we have like Meissner effect. Meissner effect. What this means is like superconductor is repelling magnetic field out of its bulk, but to repel magnetic field you have to do work. Exactly like a gas expanding on a piston has to do work to push the piston. So superconductor in the same way needs to do work to repel the magnetic field. And the question is, why would it make extra work, right? It makes extra work, right? Because it takes some work to do repel B, because it's energetically favorable. So B is repelled because of energy. So that tells us we are in like a thermodynamic equilibrium phase, and the system wants to go there, even if it costs extra energy to get there. So, and let me remind you how we think about thermodynamic variables. So this is actually a little bit well known. Let me start with that and then modify. So this du is TdS minus P dV, right? This is like entropic contribution, and this is the piston doing work by expansion. So this is for ideal gas. And similarly, so for superconductor, what I'm going to use is du is equal to TdS plus HdM. Technically, like if you are using SI units, you need like a nu zero here. There's also some volume factor is needed. And sometimes if you are using Gaussian, you may also see 1/4 pi. But to keep it clean, I'm not going to write these factors, and let's work it like this. And from here, what we see is like U is a function of entropy and magnetization. And if you want temperature, you can get it by del U del S. You can also write it is like for fixed M, but I'm not going to do that. And if you want H field, you can get it by del U del M. Good. But like in thermodynamics, it's not always ideal to work with these variables, and we can do Legendre transformation to any variables we want. For example, we can go to free energy. F is equal to U minus Ts. So this is sometimes called Helmholtz free energy. Or we can go so-called Gibbs free energy. G is equal to U minus Ts minus H dot M. Good. And by differentiating G, we can see what variables it depends on. So dG is equal to du, but du is TdS, right? Like this expression here. TdS plus H dot dm. And I differentiate here minus TdS minus dTs. And this one minus H dot dm minus m dot dh. So TDS, HDM cancels HDM, and at the end what we have is minus S dt, this term, and minus M dH. Right? How many people know this standard procedure, right? You can change the variables and go any variable you want, and from here you can see G is a variable of temperature and this external magnetic field, which is what you want, right? These are the things you can control in an experiment, and if you want, you can do del G, del T to find the other variables, S or del minus. Let me put minus here, or del G, del H to find M, and there's also minus here. Now let's think about H versus T phase diagram. So we said the typical phase diagram for like a type 1 superconductor is something like that. We can also do it for type 2, but let's keep it simple. So this is H and this is T, and you have something like this. So this is H critical line. Here you have like a superconductor. Here there's like a Meissner effect repelling the magnetic field, and here you have normal. And what I want to do is I want to integrate Gibbs free energy along this line, like this. And what I can find from here is, so in the superconducting phase, let me label it, I'm doing it in the superconducting phase, and there's like some T which is fixed, and here I have H critical minus G superconductor T0. This is equal to dG, and dG is given here, and you can see T is fixed, so I'll only have this term. So this is going to give me minus M dH. But what is M in a superconductor? We went through. Superconductor is the perfect diamagnet. Minus H. So this is minus H, and this is going to give you 1/2 H squared. Again, there is like some unit factors, but I cleaned up, not to clutter the equation. So then what we see is like GS of THC minus GS of T0 is equal to 1/2 H squared. Sorry, this is HC. We are integrating up to HC. But at HC, like here at this point, superconductor and normal metal, they coexist. That means they have the same energy. Right? That's the condition for coexistence. That means also, okay, in metals, what is M in metal? If you have like a good metal, what is the diamagnetic property of a metal? Like
something positive, I think.
What something?
It's like chi times
Yeah.
H, but chi is something like positive, but not
Like I think this is like 409 subject, but we generally cannot teach it because we don't have as much time. There are basically two contributions. One is like so-called Pauli contribution. It comes from the spins of electrons. The other one is so-called Landau contribution. It comes from like these electron cyclotron orbits. And if you calculate both of them, you find like something, but it's very tiny. Okay, the M, we can, for all intents and purposes, take M to be 0 in metals. And that means at this point, G superconductor T H critical is equal to G normal T H critical, But G normal, let me also write one more line. So this is G normal T H critical minus G normal T0 is equal to, again, this one, right, this equation. But if I put m is equal to 0, this is going to give me 0. Now I have two equations, so this one and this one. And I also have this, let me label them. This is 1, so this is the critical point 3, and this is the normal metal relation for 3. So what I want to do is I want to write this equation again. So you can see G normal T HC is equal to G normal T0. So this one, this one, G normal THC is a G superconductor is H the critical point. This is equal to normal metal THC, right? But this is at any given T, right? So at any given T, if you are here, G for normal metal and G for superconductor are the same here, because they coexist. Their energy should be the same so that they can coexist,
okay.
right? If there is like an energy difference.
I mean, there is another equation saying that this is.
So this basically, I am saying that at the critical magnetic field, G normal and G superconductor should be the same. Now I look at this thing. So this one, G normal THC, and I use this. This is going to be equal to G normal T0. And from here, I see that G normal T, and now we can forget about magnetic field. At any given temperature and without magnetic field, normal metal minus G superconductor T0 is equal to 1/2 Hc squared. So what this equation is saying is like a superconductor has this much energy advantage compared to normal metal. Okay? That's why if it is energetically favorable, superconductor wants to go and be in that phase. And this is like a positive quantity, so this is lower energy. We can also do the same calculation with free energy in the case of sometimes some books are using free energy, but our book is using Gibbs. So this is F and T, 0 minus F superconductor T0 is also 1/2 Hc squared. You can also find that. And typically, experimentally, the condensation energy is something like 2 microelectron per atom, right? So it is like a tiny energy, like the system has like, and also remember we are in Kelvin, sometimes sub-Kelvin temperatures. It's like very tiny temperature, and the amount you gain is also tiny. And we'll see this small energy difference is going to be due to like superconducting gap, energy gap. We'll show it with delta, and it will also be order of this, and it is going to be much smaller than Fermi energy. And now I can introduce, keeping this result in mind, I can introduce Ginzburg-Landau theory. So let's think about now, this theory is completely general, like superconductors, magnets, liquid, solid transition. If you want, like all kind of phase transitions you can see in nature can be described with Ginzburg-Landau. And it is very powerful, but the problem is it's not microscopic. It is like a phenomenological theory. Phenomenological approach. What this means is like you make up some parameters and you have to fit these parameters in the experiments. And the key object in Ginzburg-Landau theory is so-called order parameter. And what is order parameter is, it is something 0 for t bigger than Tc and non-zero for t less than, okay, let me put equality here, less than Tc. So that's all we know for order parameter. And for second order phase transition, we also require order parameter to be 0 at Tc. And it is equal to 0 at T is equal to Tc, so that we can assume it is tiny in the vicinity of Tc. For superconductors, Ginzburg and Landau used psi for order parameter. So in their theory, they do not specify what psi is, but they were inspired by, like, similar to helium-4. Actually, I heard a story like when the theory was initially developing, people from West, like Americans, I guess, they saw their theory and they were like kind of making fun of them, like saying like psi, because it was used for quantum mechanics in the US, and they were like using psi in a completely different context, and they were saying that psi is changing its meaning on the other side of Iron Curtain. But now, today, everybody uses Ginzburg-Landau, right? Today, it's well established, one of the most powerful approaches. Nobody has any doubt with that. So, psi is, they assumed, a complex number. And so this is another assumption. And also, they said F, the free energy, can only depend on psi, but not on the phase. There should be no phase information in the psi. Now is the point. So since psi is small in the vicinity of T is equal to Tc, they Taylor expand. Taylor expansion. And let's do that. Here is the free energy density for superconductor at some given temperature. There will be some constants, and the constant is written as like normal metal free energy at that temperature. And lowest possible value is like some coefficient A times psi squared. So we require F to be a smooth function of psi and psi star, the complex conjugate. And for that to happen, the lowest order term we can start is psi squared, and the next order term is, typically we put 1/2 here, b psi to the 4th. So now in this form it is like a differentiable, if you want it smooth, and function of psi and psi star, and no phase dependence. But we don't want anything depending on phase, because phase is not a physical quantity. And here they consider A to be, I didn't write it, but like a t-dependent quantity, and B is also a t-dependent quantity. And for free energy to be like a minimum, right? If we want like a ground state that's like a minimum, we need B to be positive. If B is negative, free energy is going to go to minus infinity, and your minimum energy is going to be garbage. In some theories, if B is negative, you need to take psi to the sixth. But those theories are a little bit more exotic, so I'm not going to do that. So for minimum free energy. Now let's take the derivative and see del F S. Let me take it to absolute value of psi. The first term is 0 plus A times psi plus 2A times psi plus 4B, right? That's 4B times psi cube, and I set this equal to 0. Oh yes, 2B, because I put 4 1/2, so this is 2B. So this is for minimum energy we are trying to find. That means psi times A plus B psi squared is equal to 0. Then there are two conditions, two cases. Case 1, psi is equal to 0, and this is normal phase. Case 2, psi squared, so this thing is 0. Let me write that. A plus B psi squared is equal to 0, and that gives yes, we'll come to that. We'll decide what A should be in a little bit. Psi squared is equal to minus A over B. And we call this is normal, this is, if you want, broken symmetry phase. So the idea is, okay, this is more general. Typically you have like a higher symmetry group, G, right? I want to leave it unspecified. For example, if you are in a in a normal metal, G can be like U1 phase, U1 symmetry. If you are in a magnet, it could be SO3, three-dimensional rotation symmetry. And as you go to lower symmetry, you break the symmetry, right? You break the symmetry to a subgroup H. H is smaller than G, and you want this action to be a member of this subgroup. You can be in the subgroup, but you break the symmetry. So that's why we call it broken symmetry phase. But this is just jargon. I think at the moment we don't need that. But if you have been exposed to it somewhere else, that's the connection. And what we see here is, of course, here we require, because of this absolute value squared, A need to be negative, and this entire object should be positive. But what we are seeing is, here is the pictures. So this is F, and this is psi. So this is F, and this is psi. And at the moment, let's assume psi is real. In that case, if you are in the high temperature phase, so this is normal, the energy is something like that, and we have a minimum at psi is equal to 0. And if you are in the superconducting phase, you have something like that. So this is super phase, and the energy is somewhere where, let me call it psi star, which is non-zero. Good. Therefore, this psi is equal to 0 for t bigger than Tc. And okay, let me do it in just a little bit. Let's think about A. So a of t should be bigger than 0 for t bigger than tc, and a of t should be smaller than 0 for t less than tc, right? Otherwise, if a is not negative, I cannot make sense of this object. And that's why, and it's also supposed to be 0, right? You need to go from non-zero to positive negative at some point, and it is like 0 point. That's why they expanded a like this. So there is a little funny notation, don't worry about this. I just copy the notation they use. They use like at times t minus tc and higher order terms. So in the vicinity of tc.
How do you conclude that the sign of A is due to T?
Because of this, right? Here, if you look at this, A above TC should be positive, so that you don't have like a minimum psi, right? If A is negative below TC, then you have this. Otherwise, you don't have it. Therefore, A is changing sign with T minus TC. And that's what they use. Like there's like a coefficient, A dot coefficient, T minus TC. And you can see if T is below TC, this is negative. If T is above TC, this is positive. And for B of T, they use some constant B and higher order terms.
Why we can't say vice versa?
Because if B is negative, right? If B is negative,
No, not B. Let's say you say this is superconducting and this is normal. This is superconducting and this is normal. Let's just change it. So it will be superconducting and this will be.
Change this one and this one.
Yes.
When you change these two, what do you change?
Just names. How we conclude that it's due to critical temperature?
So this superconducting phase we define by a non-zero psi. If this order parameter is 0, right? We say it is normal.
Why we say it's normal?
Because in normal phase there is no order parameter, there is no ordering. You can think about magnetism, right? In the magnetization, so there is like in a magnet in the refrigerator, if you are in high above Curie temperature, right, FE 100 Kelvin, M is 0. As you lower the temperature, there is like a critical point where M is non-zero. Now you have a magnet in your hand. Therefore, at low temperature, this order parameter should be non-zero, and at high temperature, it should be 0. So in our case, we at the moment have like a funny order parameter. We'll see what it means, but psi should be 0 in ordered phase, high temperature phase, and non-zero in the low temperature, broken symmetry phase. Okay.
So in T greater than TC case, we need to have A equals 0, right? Not A equals A.
Absolutely, yes. Yes.
But you then write that A greater than.
So A is greater than 0 for T bigger than TC, so that...
But A should be equal to 0, just the Q.
Yeah, exactly. At A of T is 0, at T is equal to TC. Absolutely, right? Because you need to go from positive to negative values. In the middle, there has to be a point where it is 0.
I don't get this.
Like I'm only looking at this equation, right? This equation.
Yes.
And this equation is telling me the minimum of this, right? This is like a quadratic function. I am plotting like any quadratic function. Like this is a x squared plus b x to the fourth. I assume b is always positive. And this quadratic function can be either like this if a is positive, or like this if a is negative. There is no other possibility for a quadratic function. Here, x in here is replaced with absolute value of psi. And I say that then to be like this, I need to be in the high temperature phase, then A needs to be positive. To be like this, I need to be in the low temperature phase, and A needs to be negative. That's it.
But this doesn't eliminate psi.
This doesn't eliminate psi, yes. Right? To have, so here, what is psi in that context? Minimum, let me say x star, the minimum of this function is 0 at high temperature, and x star is non-zero at low temperature. And, right, this point, wherever the minimum is, that's the corresponding to psi in our case.
What I don't get is, I mean, we expand this free energy in terms of the normal and some higher order terms. But even in the normal case, we can have some higher order terms because we didn't set A to 0.
Yes, you can have higher order terms, a c, x to the 6, and so on, but it is still going to be, the minimum is still going to be at 0.
Okay.
Right? As long as you have this a positive, put higher order terms, because these higher order terms are what? In the vicinity, it's not going to change it. The only thing that can change the sign here is this term, right? You need to make whatever, we assume this is positive. As long as this is positive, the only thing you can do is with A. And this assumption makes sense, right? Once we make this assumption, we have a picture in which order parameter is 0 above Tc and non-zero below Tc. Then this is exactly what we are making up rules, if you want. We are making up what we should get, and that so far these assumptions are making sense.
This is a continuous phase transition, right?
Yes. I didn't say anything about that, but you can also do it for like first order phase transitions, but you need like higher order terms in free energy. But typically, like if you don't know it, there are two kinds of phase transitions. They are like first order and continuous. And sometimes textbooks are going to show you like first order, second order, third order phase transition. There is no such thing anymore. We don't use it. There is actually also topological phase transition, which is infinite order. But Ginzburg-Landau is valid for continuous or second order phase transitions. And what this means is that you need an order parameter that continues to increase from 0. If at Tc there was like a jump in the order parameter, that would be first order phase transition. Exactly like latent heat, right? There's like latent heat means what? There's like a jump in some thermodynamic quantity. If you have a jump, it's not continuous. So what these assumptions gives us is exactly what we need. We have like a psi, which is 0 for t bigger than Tc, and it is equal to, let me write it, A dot over B times T minus Tc to the power 1/2 for T less than, okay, let me write it the other way. So this is Tc, T less than Tc, and if you, the picture is something like that. This is psi, this is Tc, and you have like a T is equal to Tc, and your order parameter is 0 here, and as soon as you hit Tc, it starts increasing, and it is something like that. Good. So note, so psi is going to be a norm of psi times e to the I theta, and at the moment there is no role for theta, and phase theta is arbitrary, but we'll see that it is going to be related to the so-called XY model phase. That's why superconducting phase transition is in the same universality class with XY model. And this is kind of like, if you want a magnet, but a magnet in a planar, like 2D planar complex plane. Now let's find the value of minimum value of free energy so we said F superconductor is equal to F normal plus A psi squared plus 1/2 B psi to the fourth, and I will put psi is equal to minus A over B, and this one will give me Fn minus A times A over B plus 1/2 B times A squared over B squared.
Why minus?
Because this is A positive, this is negative.
It's squared.
Yes, yes. Right? Oh, so this is square, yes. This is square, yes. Then this is F normal minus A squared over minus A squared over B plus 1/2 A squared over B, and this is minus 1/2, right? Minus 1/2, and I can erase this. So you can see this is positive, 1/2 is positive, and superconducting phase is lower energy. Exactly like where we started earlier in the class. And earlier what we found was Gibbs free energy, but we said we can also obtain it from the Helmholtz free energy. And the energy difference was there, hc, right? It was like 1/2 hc2 squared. And I can say, okay, now the amount I gain should be the same. Then I have one relation for my phenomenological parameters. A squared over B should be equal to 1/2 hc squared. And if I can find another relation, I can eliminate all arbitrary parameters. Or another way to look at this, you can solve this equation for hc, and what you find is hc is equal to a over root b, and in terms of earlier a dot for b, this is tc minus t. And you can see we are seeing the critical field is 0 in the normal, and it increases linearly as you enter the superconducting phase. We can also calculate other thermodynamic variables. Let's consider entropy. S is del F del T. Then S superconductor is going to be, right, the del F del T superconductor. Del F del N, I'll write it as normal. And this will be, and we assumed B is a constant. The only temperature dependent thing is here AT. Therefore, this thing will be del A del T times psi squared. Therefore, the S superconductor minus S normal phase is going to be equal to minus A dot squared over B Tc minus T. So what this says is superconducting phase has lower entropy, right? So this one has lower entropy. So that means you are more ordered, right? If you are more disordered, you have higher entropy. And this will make sense as we see more about superconductivity, that this is so because you have like a kind of like a condensate, and this condensate freezes some degrees of freedom. Like there's like so-called particle Hall excitations in the normal metal, and once you enter the superconducting phase, they are frozen out. So you have less degrees of freedom, you are more ordered, and less entropy. But you reduce the entropy by changing the phase. Let me do one more thing and I will finish. This is last thing.
Hocam,
Uh-huh.
A dot is plus or minus?
So A dot, if you go up, it is positive, right? That's how we defined here. So we said A of t is some A dot times t minus tc. A of t, we require it to be positive above tc and negative below tc. For this to happen, this needs to be positive. Yes, yeah, that's a good point. Thank you.
Then, H, the formula for H is determined.
This one?
It's
So-
negative or positive? Because A is negative.
So above
No,
t,
A, not A dot, but A is negative, isn't
A is negative, yes, yes.
Then shouldn't be there minus sign? Like minus A over square root of B.
Let me check what I did here. I put TC minus. So I think first this looks correct, right? This looks correct to me because in the superconducting phase, HC should be finite, like a positive quantity, and TC minus T, because T is lower than TC, this is positive,
Yes.
this is positive, this is positive, that makes sense. And your question is like, if I think
Minus A over square root of B.
exactly, I think this should be minus, right? Yes, thank you. Because this has like two roots, I need to pick up the yes. Good job, thank you. So lastly, let me consider one more thing and I'll finish it there. Let's also consider the specific heat. And CV is equal to T del S del T. And from here what we see is CV normal minus C, let me write first superconductor minus normal is equal to some T times A dot squared over B for T less than TC. I just didn't do anything, I just take the derivative here and write, that's exactly the thing. And above it is 0 for T bigger than or equal to TC. Let's sketch this and then finish it there. So here is TC. Let me also test your condensed matter StatMech. So what is the specific heat for metals as a function of temperature? Right? That's like a very common question for qualifiers and things like that. Like T cube. What are the contributors? So what contributes to specific heat? That's when you open like a condensed matter book. That's what you start with. They're like phonons, but what else? They're also like an electron gas. Right? At low temperatures, there are no T cube is phonon. You are right. At low temperatures, you can forget about that because we are in Kelvin temperatures. They are phonons. They have their roles, but they don't have any contribution to specific heat. What else? This is actually not condensed matter. If anybody took any StatMech, we also kind of talk about something called Sommerfeld expansion.
I think it was
Not the Drude, like Drude model is for connection. So if typically we show it like this, CV is CV over T is equal to some A plus B T squared. Right? At least Kittel is using it like this for some coefficients. This one is phonon contribution. This one is electron contribution. And at low temperature, it is linear in T. I mean, you can look at Kittel. It is not very difficult, but the idea is, so it goes linearly above TC. There is like some coefficient here. If you want, this is like gamma times T, and that comes from Sommerfeld theory of metals. And you can see as soon as you hit TC, there's like a a change in the slope, and specific heat is going to increase. Like there's like a jump, and there's maybe a different kind of slope here. And here, there's this A dot squared over B times T. and the amount of discontinuity, so jump in TC in C, let me call it delta C, is equal to linear T times A dot over B. Now we have like a third example for specific heat, right? We had like Bose condensates. In the Bose condensate, it was like a kink. In the superfluid helium, it was like a lambda transition, and there was like some logarithmic dependence. There were like some universal exponents. And here, this is also not like any of those. But still, this is like very like baby theory. We are going to improve that with more complications later, but that's what we have in our hands. Any questions? All right, thank you.